Alright, in this numerical example of analyzing a machine or frame, this would be a frame because it's not mobile. Machines are mobile. We've got a system that has this 150 Newton load out here at a 45-degree angle from the vertical. Now, one of the variety of things we have got to absolutely do, and that is solve only what's actually been requested here. We want the magnitude of the resultant forces in the pins at C and D. Right, so there's C and there's D. Right? They're not asking us to find the reactions, so let's not find them unless we absolutely have to. Right now, of the variety of things that we got to do, of course, step 0 is figure out what the find is. Find the find. Right? Step 1 really now is identify how many members. Do you understand or interpret the drawing correctly? Right, so in this system we got 1, 2, and 3 members. Right, only 3. They're not joint to joint. They're where the pins are at. Right, so unless we're told otherwise, we have solid pieces until so like this L bracket here, A, B, C, D, should be interpreted as one long continuous piece that just so happens to be pinned at A to the external support, pinned at B to an external support, has another member pinned at C, and another member pinned at D. Right? And then we want to identify 2 force members. Right, now remember, the way we do this is pretty simple. If they have only 2 pins, and they have no other forces applied to them, they must be a 2-force member, such as ED. So we'll show that. Remember real quick, it's a little short link. It's only got pins at E, pins at D, and notice sum of moments, that is, about E tells us that dx has to be 0. Sum of moments about d tells us that ex has to be 0. So therefore, this has to be a member that's either in compression or in tension. So note, if we were to pull the pin at D, this whole system that would be left over would want to spin about point C going in a clockwise fashion. In other words, it would want to try to squeeze that member. So if we put it back into place, it's got to be in compression. And that's then what's going on with that short link. That's crucial when we come back to what we've got down here for this free body diagram of this whole little piece. Right, so there's your D, and then over at C we pulled a pin. This is a multi-force member, so I don't know initially what those components are going to look like. CY and CX, they're just independent. But note, on this subassembly here, I've got the applied force of 150 newtons. We have the internal force at D, which is the pin force at D, and it looks like we have 2 forces at C, but those can be resolved into a single force, right? A force that has magnitude and direction, and that means we have a 3-force member, and a 3-force member must be a concurrent force system, meaning that all the lines of actions of the forces must pass through a common point. And so that means we come down here, this is really 45 degree, so that's 100 here, 100 there in millimeters, and even though that's not quite exactly to scale, it tells us what has to be happening, that CX, CY must resolve to a line of action that passes through there. And the only way to do that is if CX and CY both point towards C or they point away from C. Let's see what might really be happening. Right? We don't know yet, maybe. I can anticipate what's going to happen, but that's because I've actually looked at this problem a number of times, right? So I'm cheating. Alright, so let's get our 150 newtons roughly at a much better scale of 45 degrees, which is where it's at for our analysis. There's 150 newtons. We know that D is vertical, and then all I know is, I do know it's going to be going up, and tip to tail construction, the force triangle means that C has to be coming downwards to the right, there's your D, there's your C, and so that means CX, CY have to both be pinching towards point C to get this downwards to the right, so that this force triangle goes around in the circle, closes off, circle goes around in the triangle. That turns out to be 90 degrees. That's just happenstance in this situation, right? Because that was 100 down, 100 over, 100 down, and then we go 300 over to point C, and to go up to point C we had 200 to that dashed line, and then another 100 to get to that location, and that meant that we had 300, 300, or 45 degrees. That's how I knew that, which meant that with that being 45, and then we said this is 45, so therefore that's 90, and then that makes it actually really easy to figure out. This is a statement of equilibrium. C will have to be equal to 150 newtons, and D will have to be equal to 150 root 2 newtons. Right now, because we're only asked to find the magnitude, not the direction, but the magnitude of the resultant forces, then that's a complete answer for the what we've been asked to actually find.